Okay, today let's have a look at the fourth lesson of chapter 6, intersection of lines and planes. First of all, let's have a look at today's learning goals. So after this lesson, you are expected to be able to understand that in 3 space, there are 3 possibilities for the intersection of a line and a plane and related system of equations. Next, given a line and place in 3 space, determine if the line intersects with or lies on or is parallel to the plane. Then find the coordinates of the point of intersection between a line and a plane in 3 space if applicable. Next, find the distance from a point to a plane in 3 space. And last, find the distance from a line to a plane if the line is parallel to the plane. All right, so first of all, let's have a look at the intersections of lines and planes. So in 3 space, there are 3 possibilities for the intersection of a line and a plane and the related system of equations. So first, the line could intersect the plane at a certain point. The system has a unique solution, which is shown on the graph on the left. The second possibility is the line could lie on the plane. Then the system has infinitely many solutions. Third, the line is parallel to that plane. Accordingly, the system has no solutions, which is shown on the graph on the right. Okay, so these are the 3 possibilities for the intersection of a line and a plane. Okay, I'll give you a minute to have a look at these concepts here, and then we'll have a look at some examples, okay? Okay, now let's have a look at an example. In each case below, determine if the line and the plane intersect. If so, determine the solution. Okay, I'll give you 6 minutes to have a look at these 3 questions, and then we'll have a look at the solution together, okay? All right, have we finished? And let's have a look at the solution here. Okay, first question. To check if the line and the plane intersect, we can combine these two equations to form a system and try to solve the system. So we can substitute the parametric equations into the scalar equation of that plane. Then expand and solve for t. That gives us t equals -1. Since a single value of t could be found, the line and the plane must intersect at a single point. Then substitute t equals 1 in the parametric equation, which gives us x equals 3, y equals 0, and z equals -1. Therefore, we know the line and the plane intersect at a single point whose coordinates are 3, 0, and -1. Okay, any questions? All right, if no questions, let's consider question B. Again, we can substitute the parametric equations into the scalar equation of the plane, which gives us 4 plus 6t plus 3 times -7 plus 2t, that's the y coordinate, right? Minus 4 times the z coordinate, which is 1 plus 3t equals 10. And you can find that actually 0 times t equals 31. Therefore, there is no solution for this equation. Since there are no values of t that make the equation true, the plane and the line do not intersect because you can't find any single solution that satisfy the equation for the plane, right? Therefore, we know the line is parallel to and distinct from the plane. Okay, any questions? All right, if no questions, let's consider the next one. Again, in question C, to check if the line is intersecting or coincident with the plane, we can substitute the parametric equations into the scalar equation of the plane. That gives us 0t equals 0. So as you can see here, any t that belongs to the real number set can fulfill this equation, right? Which means this equation is true for all values of t. So any point on the line is a solution, which means the line must lie completely on the plane. All right, any questions? All right, if you don't have any question, let's consider another example. So without solving, determine each line intersects the plane or not. First pair is L1 is given by this vector equation. 2, negative 5, 3 plus s times 3 to 1. And the plane pi1 is given by a scalar equation 3x minus y plus z equals negative 6. In question B, the line is given by this vector r equals 1, 0, 1 plus t times negative 2, 1, negative 4. And the plane pi2 is given by a scalar equation 4x minus 2z equals 11. Okay, I'll give you 5 minutes to consider this problem by yourself. Then we'll have a look at the solution together. Okay, now let's have a look at the solution to question A. Okay, so note that the direction vector of the line is m, whose components is 3, 2, 1, right? You can directly read this from the vector equation of this line. And from the scalar equation of that plane, we can see the normal vector of the plane is n, whose components are 3, -1, 1. So now let's examine the dot product between the two lines to check if they are perpendicular or parallel, or is not perpendicular nor parallel. Okay, so the dot product between the two vectors is 3 times 3 plus 2 times -1 plus 1 times 1, which is 8, right? Since the dot product is not 0, therefore we know m and n are not perpendicular. Therefore, we know the line and the plane are not parallel, so they must intersect. Okay, any questions? All right, no questions. Let's consider question B. Okay, again, we can find the direction vector of this line is m, whose components are -2, 1, 4, right? You can directly read this from the vector equation of this line. And the normal vector of this plane is n equals components 4, 0, -2. You can also find this directly from the scalar equation of this plane. Then again, examine the dot product to check if the two vectors are perpendicular. So dot product between m and n, if you calculate this, you can see that that's actually 0, right? If the dot product is 0, we know the two vectors are perpendicular with each other. Therefore, the line and plane are parallel and can be either coincident or distinct. Then let's test a point on the line, which is 1, 0, 1, to see if it's also on the plane. So substitute these coordinates into the scalar equation of that plane. Well, apparently the right side is 11, right? And the left side equals 1 times 4 times 1 minus 2 times 1, which equals 2, which is not equal to the right side. Therefore, the point 1, 0, 1 does not lie on the plane. So basically, if you have a line that is parallel or coincident with a plane, and you can also find a point on the line is not on the plane. Therefore, we should know the line and the plane are parallel and distinct. Okay, any questions? All right, if you have no questions, let's consider another key concept of this lesson, which is a distance from a point to a plane. So if a line and a plane are parallel and do not intersect, it is reasonable to ask how far apart they are, right? The shortest distance is the perpendicular distance. Since the line and plane are parallel, we need to find the perpendicular distance from any point on the line to the plane. So in order to find the distance between a parallel line with a plane, Well, actually, you need to find the distance between any point on the line to that plane, right? So that actually converts the problem to the distance from a point to a plane. So next, let's have a look at example. Can you find the distance between the plane whose scalar equation is 4x plus 2y plus z minus 16 equals 0 and each point below? First of all, point P whose coordinates are 10, 3, and -8. Then in question B, we have a point B whose coordinates are 2, 2, and 4. Okay, I'll give you 5 minutes to have a look at these questions. Okay, have you finished? Let's have a look at the solution together. For question A, first, you can check if the point P lies on the plane or not. So substitute the coordinates for point P to the scalar equation of that plane. The right side is 16, right? Left side is 38. Left side does not equal the right side. So the coordinates of point P does not satisfy the scalar equation of that plane. Therefore, the point P does not lie on the plane. So also note that a normal vector of that plane is n whose components are 4, 2, 1. So we can choose any point Q on the plane by selecting arbitrary values for x and y, right? If we select x equals 4 and y equals 0, then z equals 0. So Q 4, 0, 0 is a point on the plane. This situation is illustrated by the graph on the right here. Of course, you can choose some other point on that plane. As long as your point is on that plane, you'll be fine, right? And next, we can find the projection of vector PQ onto the normal vector N. Well, actually, the distance of the projection or the magnitude of the projection vector is the distance d we require, right? So first of all, we find the vector PQ, which is vector OQ minus vector OP. And components of vector PQ are -6, -3, 8. So according to our discussions, the distance d we require is the magnitude of the projection vector, which is given by the absolute value of the dot product between n and PQ, or PQ with n, over the magnitude of vector n. So we know the components of vector n. We also know that components for vector PQ. So put all the values in, we have 22 over square root 21, which is approximately 4.70 or 4.80, right? Therefore, we know its distance from point P to the plane is approximately 4.8 units. Okay, so what's the main takeaway of this example? The main takeaway is the distance between a point P and the plane can be given by the following formula. D equals the magnitude of vector PQ on vector N, which equals the absolute value of vector PQ dot product with vector N over the magnitude of vector N, where Q is any point on the plane and N is normal vector of that plane. So you might want to write this down onto your notebook. Okay, so have a look at this question. Do you have any questions? All right, if you don't have any questions, let's have a look at question B. Again, first we can check the coordinates of point B, 2, 2, 4 in the equation in the plane of the plane. So the left side is 16, which is exactly the same with the right side. So point B is also on the plane. If the point is on the plane, then the distance between the point and the plane should be 0, right? So it is 0 units from the plane. Also note that the formula we obtained in question A is still applicable in this case. For example, we know Q400 is on the plane, right? So vector BQ is 2, -2, -4. Then a normal vector of that plane is n, which is 4, 2, 1. And using that formula, distance between these 2 points is actually the magnitude of the projection vector BQ on n, which is given by the absolute value of vector BQ with a dot product with n over the magnitude of vector n. If you put all the values in, you can also see that distance is actually 0. Therefore, we should know that the point is on the plane. Okay, any questions? Okay, if you don't have any questions, let's make a summary of today's lesson. So after this lesson, now you should be able to first understand that in 3 space, there are 3 possibilities for the intersection of the line and the plane and related system of equations. Then given a line and plane in 3 space, determine if the line intersects with or lie on or is parallel to that plane. Then find the coordinates of the point of intersection between a line and a plane in 3 space if applicable. Next, find the distance from a point to a plane in 3 space. Last, find the distance from a line to a plane if the line is parallel to that plane. Well, for the last aspect, actually you can choose any point on the line that is parallel to the plane, and then to calculate the distance from that point to a plane. That is the distance between line that is parallel to the plane, right? Okay, so that's the end of today's lesson. Remember to complete the homework on Google Classroom and submit them before the deadline, okay?